chi-square goodness of fit tests. Okay, in chapter 5, we looked at the binomial distribution, which we used to analyze experiments or trials that had only two possible outcomes. So we were looking at categorical data, so yes or no, or success or not success, and we looked at the counts. So an extension of this problem is a multinomial distribution in which more than two possible outcomes can occur. So the chi-square goodness of fit test is used to analyze probabilities of multinomial distribution trials along a single dimension. So what does that mean? What we're doing with the chi-square goodness of fit test is we are going to compare the expected frequencies or the expected counts, which are the theoretical, of categories from a population distribution. We compare those to the observed counts, the actual frequencies, from a distribution, so that's the sample data, to determine whether there is a difference between what we expected to see and what we actually saw from the sample data. The null hypothesis then is that the two distributions are the same, so the theoretical and the empirical, which is the observed, versus the alternative hypothesis is the two distributions are not the same. Okay, so there's some cautions we need to look at first. So when the expected value of a category is small, a large chi-square value can be obtained erroneously, and this leads to a type 1 error. So to control for this error, the chi-square goodness of fit test should not be used when any of the expected frequencies is less than 5. Okay, so how do we calculate the expected values? Here is the formula for the chi-square test, and it is equal to the sum of f sub naught. So that is the observed counts right here. And then the expected counts, what we would expect to see, squared, divided by the expected counts. Okay, and the degrees of freedom that correspond to this is k, which is the number of categories that you are looking at, subtract 1. Okay, so f sub naught is the frequency of observed values or the observed counts, and f subscript e is the frequency of expected values or the expected counts, and k is the number of categories. All right, so how do we do this? So first step is compute the expected counts given a sample size and the probability specified by a null hypothesis. 2, we then calculate the chi-squared statistic, right? That was the sum, and its degrees of freedom, so k minus 1, and also the critical value. Now the critical value comes from the table, and we usually use 0.05 for a significance level, and then we compare that to the chi-square test statistic. Then we interpret the results. Okay, so if the chi-square statistic that we calculate is greater than the chi-square star from the table, that's the critical value from the table, then we reject the null hypothesis. If it is not greater than, then we do not reject the null hypothesis. So let's look at an example. We have the demographics of customers example. So a company's products are marketed to a population that consists primarily of young customers. So the table here shows the age distribution of customers and for the past several years. So from 12 to 17 years, we have 35% or 0.35. From 18 to 24 years, we have 50%, 0.5. And 25 years and over, their age is 0.15 or 15%. So a random sample then of 300 current customers received a survey that asks about their age and other demographics, and the results of 273 that responded. So that's a nice high response. So 300 surveys were sent out, 273 came back, and the results are shown here in the table. How well does the age distribution in the sample of current customers match the age distribution of customers from several years? So this one here is from several years, And then this is the recent data to see if it's changed. So what we can do is run a chi-square test, chi-square goodness of fit test, and see if the age distribution has changed. Okay, so we'll keep those values. I'm just going to switch screens here so we can write those out. All right, so the expected count we can calculate for ages 12 to 17 rather, is equal to, so you take 0.35, that was from what they had, that was from the frequencies of several years, and you multiply that by the total number in your sample. There were 273 people that responded, and that ends up being 95.55. So that's the expected count. Now that's a lot higher than 5, so that's good. Then we can do this for the next age category, for 18 to 24. So for 18 to 24, you would just go, so I'll just put here 18 to 24 category. That's going to be equal to, now there was half of those, times 273, ends up being 136.5. So these are the numbers that we would expect to see. So these are the expected counts from a sample of size 273. So then 25 or more, so age 25 or more, oops, don't know why I put that, more or greater than, that's going to equal, now their range was for several years was 15. So if you have it right in front of you, it's easier to do. I'm just sort of going back and forth here. Okay, that ends up being 40.95. All right, now we have the expected counts and we have the observed counts from the second table, and we can calculate the chi-square. So the chi-square ends up being, chi-square ends up being the sum. So we take the first group, so ages 12 to 17, their observed count was 78 from the sample. You subtract what we would have expected to see, so 95.95. We square that and divide by the expected counts. Add it to the next group. So the next group, we observed 158, right, out of 273. They're expected, we would have expected from a sample of that size 136.5 and divide by 136.5. So don't forget to square the numerators. The top one is 37, subtract 40.95 squared divided by 40.95. So it's always observed. I think of it this way: observed, subtract expected, squared, divided by expected. Or the notation in the text, the frequency of the observed, subtract the frequency of the expected, squared, divided by the frequency of the expected. So it's the same thing. All right, we plug all those values in and we get 6.99. And we can now go get the table. So just remember 6.99 is our observed test statistic. It's the chi-square statistic. We will go back to the table. We need the critical value. And so K, there were 3 categories, right? We have K equals 3. So K subtract 1 is going to equal 2. So we want 2 degrees of freedom, and 2 degrees of freedom with 0.05 is 5.9915. So remember, our chi-square test statistic was equal to 6.99. And so we do have, so we can conclude our chi-square is greater than our table critical value of 5.9915, and therefore we reject the null hypothesis. Okay, so what does this actually mean in terms of what we were looking at? So I'm just going to go back to here. How well, here was our research question right here. How well does the age distribution in the sample of current customers match the age distribution of customers from several years? So how does this distribution of several years compare to the recent or current distribution? So we rejected the null hypothesis that meant that they're the same. So we would conclude then that the observed counts, that's these ones here, of the current years are not compatible with the hypothesized proportions. So the data then provide evidence that the age distribution of the customers has changed. All right, so that's how you conduct a chi-square goodness of fit test.